Hello and welcome to Cannon County High School Algebra 2. Does order really matter? Sometimes order matters and sometimes order doesn't matter. Yesterday we used the counting principle to figure out the size of a sample space of a given problem. Today we're going to expand on that and use something called permutations and combinations to let us also figure out different sample spaces that we'll later on use to calculate probabilities. So Mr. Lyon, I'm going to ask you to sit over here for just a minute. And we are going to first talk about a problem that we could have done yesterday. And that's using the counting principle. What I'm asking you to do is, how many ways can you deal all four cards if the only four cards you have to deal are the ace of diamonds, the two of diamonds, the three of diamonds, and the four of diamonds? Let's say we're going to start out making this problem a little more simplified than if we used all 52 cards. If these were the only four cards in the deck, how many different ways could you deal out the four cards? Well, you could shuffle them up first, and you'd shuffle them around. And let's say the first way you did it was you got the two, and then the ace, and then the three, and then the four. And then you picked them up again, you shuffled them up again like this, and now you got the three first, and then the ace, and then the four, and then the two. Well, how many different ways can you do that? And that's what I want you to figure out. And one way you could do that is to actually write out the entire sample space. I wouldn't recommend that you do that, but you could, right? And I actually did it. So find the sample space. The way I did it was, first, I wrote down all the possibilities if the ace was the first card that you were putting down. If the ace was the first card, then you could get the two and the three and the four, or the two and the four and the three, or the three and the four and the two, and so on and so on and so on. And then I figured out, well, what would have happened if the two was the first card? And what would have happened if the three was the first card, and the four was the first card, and so on and so on. And you can see that when you write out the entire sample space, there are 24 different ways to do this. But last video, you learned a better way to calculate that, and that is by using the counting principle. And the best way to do this is to just ask yourself, after you shuffle up these cards, how many choices do I have for the first card that you're dealt? You have 4 choices. Once that card is dealt, how many choices do I have for the next card? 3. And after that card is dealt, how many choices do I have for the next card? 2. And then finally, I only have 1 choice. And 4 times 3 times 2 times 1 is 24. And that's a much easier way of solving the problem than actually writing out the entire sample space like I did up here. But it leads us to some notation that you may or may not have seen in another math class, and that's called a factorial. What is a factorial? A factorial is this little exclamation point right here. And when we took 4 times 3 times 2 times 1, we really found 4 factorial. And factorial just means you take a number and you multiply it by all the numbers lower than it all the way down to 1 and see what you get. It's something that pops up in probability and statistics quite a lot. And so your calculator actually has the ability to find factorials. So let's do that. And some of you maybe know this already, but what I'm going to do first is I'm just going to hit 4, and then I'm going to put that exclamation point at the end. So where do I find that? Go to the math button right here, and you'll see that some choices come up. The 4th choice is PRB, which stands for probability. So if I go over to probability, you'll see that the fourth choice there is the factorial. So if I choose choice 4, I get the exclamation point right after the 4, and that really stands for 4 times 3 times 2 times 1. So I hit enter, and I get 24, which is just what we thought we were going to get. So we're going to use that factorial later on. And now, let's try to make the problem just a little more complicated. Let's say now you have all 52 cards, and you're going to play a game where you're going to be dealt 5 cards. How many 5-card hands are possible? So what you're going to do, think of it this way. You're going to take a deck of 52, and you're going to shuffle them up. I'll do that one more time. You'll have to excuse me because I'm not very good at that. So you shuffle up all 52. You can see I'm really not very good at this, but you get the idea. All right, they're all shuffled up. Now, how many different hands are possible? And by hand, what I mean is you're dealt 5 cards. 1, 2, 3, 4, 5. How many different hands are there that you could possibly get? I got the 6, ace, queen, 4, jack. How many different hands are possible? Well, just like the previous problem, you could use the counting principle and say, well, how many choices did I have for the first card? This first one where I got the 6 of hearts. There were 52 cards that I had to choose from. And then before I got the ace of clubs, there was not 52 cards left in the deck because the 6 of hearts was gone already. So that means that there's only 51 cards left to choose from. All right, and then after those 2 cards were dealt and I got the queen of clubs, there was only 50 cards left, and so on, 49 and 48. So the number of hands possible for 5 cards would be whatever you get when you multiply all of these together. And that comes out to 311,875,200. And no, I didn't do that in my head. I'm not that smart. I just calculated it earlier. That is what you get when order matters. We talked at the beginning of the video about sometimes order matters and sometimes order does not matter. Now let me ask you this. When you get your hand, does it matter to you that the 6 has to stay there and the 4 has to stay there and the jack? No, what's the first thing you do when you get your hand? You start putting them in order. Some people like to put them in numerical order from, lowest to highest. Some people like to keep the suits together. Some people like to make sure the red ones are on the right and the black ones are on the, it doesn't really matter. But you don't have to leave them in that order. So this problem, this number is too big, isn't it? We have to divide this number by all the different ways that you could rearrange these cards in your hand. Because in the problem I'm asking you, order actually does not matter. This number is too big. So how do I figure out how many ways there are to arrange these cards together? You kind of have to do a separate little problem where you say, how many choices do I have for the card that goes furthest to the left? You have 5 choices. And once I've decided that that card goes over there, how many choices do I have for the next card, and the next card, and the next card, and the next card? Exactly, you really have 5 factorial. And 5 factorial on your calculator, well, let's calculate that. What is 5? Let's see, then I hit the math button, go over to probability, choose choice 4, 5 factorial, what's that equal to? It's 120. So this is 120. There's 120 different ways that you can rearrange the 5 cards that are in your hand. So if I take the 311,875,200 and divide that by the 120 different ways there are to arrange the cards in my hand, I get 2,598,960. And for this one, order does not matter. And there are 2 different vocabulary words you need to know for each one. For whenever order matters, that is what we're going to call a permutation. And whenever order does not matter, we're going to call that a combination. So just remember that on a permutation, order matters. On a combination, order does not matter. And you can see there's over 2.5 million different ways to deal out the cards. And that's, so it's still a really big number, but it's not as big as if it mattered if the order actually made a difference, okay? Now we're gonna use some formulas for this. And here is the first one. The first one is for combinations. And this is when order does not matter. And that's really what we did on the previous problem. When order does not matter, here's what the notation looks like. You have a capital letter C, and you have N on this side and R on this side. You can have N is like the total number of things to choose from, and R is how many you're choosing. So this is called n choose r, but the C doesn't stand for choose, it stands for combinations. And the formula is n factorial divided by r factorial times n minus r factorial. Okay? And really, this is what we calculated. Remember on our previous problem when we said we had too many and we had to divide by 5 factorial? That is what we were choosing right there. So let's say we were going to do this problem and you wanted to figure out, well, what is 52 choose 5. We already know that the answer should be 2,598,960. But we're going to have to do this using this formula now. So let's figure that out over here. That would be, let's see, n is 52. So that's 52 factorial divided by 5 factorial times 52 minus 5 factorial. So I'm going to type all that into my calculator, and we'll see what we get. So let's see here, 52 factorial divided by, I'm going to use parentheses for this so that it all goes in the denominator, 5 factorial times, well, let's figure out what is 52 minus 5. That would be 47, right? So let's just type in 47 factorial. That'll be easier. 47 factorial. And when I get my answer, I get 259, what did I say it was? 2,598,960. Why it is having, this would round off to 60. Why it's rounding off to that, I don't know. But if we rounded it off, we'd get the right answer. Okay? Wait, why are you yelling at the computer? You saw what? Where? Here? Math? Aha, wait a minute. N choose R, there it is. Can our calculator do this automatically? Well, let's try. Let's choose choice 3. It puts the C there and it puts the cursor right there. So let's try 52 and we'll use the right arrow key and let's put the 5 right there. Aha, can our calculator do this on its own? 52 choose 5 where the order doesn't matter. Let's see what we get. Aha, 2,598,960. It's exactly the same answer. Why we got this, I don't know. Well, this was a free app on the phone, so we can't ask for too much. But we get the same answer, and our calculator can do it for us. Well, that's wonderful. Let's do this. Let's try a different formula. This one is for permutations. And here's where order does matter. And remember, on the previous problem, when we said that order did matter, we should get 311,875,200. So let's do the same problem. That would be 52, choose 5, but this time it's a permutation. So that's going to be 52 factorial divided by, well, what is 52 minus 5? Again, that's 47. Let's put the 47 right there. 52 factorial divided by 47 factorial. 52 factorial divided by 47 factorial, and we get, and again, it rounds it off really strangely, but see how we get the same number that we had before, 311 million and so on? Yes, and you're still yelling at the computer screen. Why is that? Because when I go to math and I go over to probability, yeah, not only can it do combinations, but it can do permutations also. So let's do that. Choose choice 2. We'll put 52 there, and we'll put 40, let's see, no, this is 52 choose 5, isn't it? So we'll put the 5 right there. So notice, this one, now we're doing a permutation. Hit enter, and there's my answer, 311,875,200. It's the same answer we got before. So this formula is what you use for combinations. This formula is what you use for permutations. And your calculator can do it for you. Now, of course, it's important that you understand how to use the formulas, but of course, since it's on your calculator, you're probably going to use that, okay? So now that you know that, let's use this to find some sample spaces. The hard part today is not doing the calculations. The hard part today is figuring out, does order matter or does order not matter? Is it a permutation or is it a combination? Because in the probability problems you're going to do later on, that's really that's what it all boils down to. So let's try a couple. Now that you know how to figure these out on your calculator, you've got a school locker, and your school locker has a combination of 3 numbers. And I don't know if this is true, but I think the numbers are from 1 to 36. So as you spin the lock, you've got from 1 to 36 to choose from. If it's not right, just bear with me. We're just going to simplify this problem down to this. So does order matter or does order not matter on a school locker combination? Well, it says combination. Combination means that order doesn't matter. But let's think about this. What if your combination was 24, 18, 32? Let's say that was your combination. If you go up to your locker and start spinning and you go 18, 32, 24, is your locker combination going to open? No, it's not, because you know that when you do the locker combination, order does matter. You have to go 24 first, and then you put 18, and then you put 32. It matters. So when they call it a combination, it's actually not a combination. It's actually a permutation. So for this problem, order does matter. So we're going to be using a permutation. You've got 36 numbers to choose from, and we're going to choose 3 of them. Okay? So let's give that a try. Hit math, go over to probability. Oops, a little too far. We're going to choose permutation, which is choice 2. And we'll put 36 on this side, and we're going to put 3 on this side. And when we do that, we get 42,840. 42,840. So the sample space for this problem would be 42,840. Is the school in any danger of running out of lockers? No, not unless we get a lot bigger, because there's 42,000 different combinations. So vocabulary matters. This says combination, but what should they really call them? When you say to somebody, hey, what's your locker combination? What you're really saying is, what's your locker permutation? Because the order does matter. Why it's called combination, I don't know, because it's actually a permutation. But don't fight it, just go with it. It's all right. Let's try another one. Let's say you're the gym teacher, and you have a gym class of 25 students. And you're going to make up some teams here. You're going to put 5 students on a team for whatever game that you're playing. The first team that you're going to have is going to be the blue team. How many blue teams are possible? How many blue teams are possible? Well, let's say you choose, let's say these are like the people in your class. After you choose your 5 people to be on that team, there they are. There's my 5 people that are on the team. Does it matter what order they go in? Does order matter? Does it matter that this one was chose first and this one was chose last? It really doesn't. As long as they're on the blue team, they're on the blue team. So order doesn't matter. So for this one, we're going to use a combination. Combination of 25, choose 5. All right, let's try that. 25, choose 5. We're going to hit math, go over to probability, choose choice 3. All right, so we've got 25, choose 5. And it comes out to 53,000, oops, you can't see that, 53,130. 53,130. So sometimes order matters, sometimes it doesn't. In this case, it didn't matter. All right, last problem, I promise. You're a baseball manager. You've got 20 people on the team. This problem is going to illustrate why being a baseball manager is, I think, the most difficult job in all of sports. How many batting lineups are possible if there's 9 batters on the batting lineup? Well, you got 20 people to choose from. I'm going to use cards again to illustrate. Let's say you got 20 people to choose from, and you want to pick 9 batters for your batting lineup. So you choose 9 people to be on the batting order, 4, 5, 6, 7, 8, 9. So now there's your 9. Does the order matter? Or does it make no difference at all? Well, let's see. Number 4 is this person gets a lot of base hits and they're really, really fast. So I want them to be first. And let's see, number 10 is just an absolutely good overall hit, probably the best hitter on the whole team. So I want number 10 to be third. And Queen here, lots of home runs, big time power hitter. We're gonna have Queen be fourth. Does order matter when you're selecting a batting lineup for a baseball team or a softball team? Absolutely it does. It makes a big difference what order you put those batters in. So since order matters, you have to use a permutation. So this is going to be a permutation of 20, choose 9. Okay? And so what is 20, choose 9? Well, let's get out the calculator again. Let's see. We're going to use choice 2 and make it a permutation. We're going to have 20, and we're going to choose 9. And you get, that is a big number. Let's see, I'm gonna write this down. You get 609 493 24800. Let's put some commas in there. Comma goes there and there and there. Almost 61 billion. There are almost 61 billion different batting lineups. How many of those 61 billion are the correct or the best batting lineup? There's only one best lineup. And it's your job as the manager to figure out which of these almost 61 billion lineups is the best one. And that's why I think being a baseball manager is the toughest coaching job in all of sports. All right, what I'd like you to do is, if you want to, go to CC4 on IXL, and they're just going to ask you to calculate some permutations and combinations. They're not even going to be story problems like this. They're just asking you to calculate some of them on your calculator. So it's not bad practice to do. I wish they would have given you some better problems, but at this point, all we're really doing is finding how big the sample space is. Later on, we're going to use that to actually calculate some of these probabilities. So anyway, thanks for watching, and I will talk to you tomorrow.